Hello, my name is Gustavo Rama, and I will be presenting the paper Computing Paramodular Forms. This is a joint work with Gonzalo Tornaría from Universidad de la República Uruguay. Okay, so we are interested in computing paramodular forms, which are single modular forms for the paramodular group. Our method is similar to the one that Birch gave in '91 to compute classical modular forms of weight 2 using some heck action on the classes of ternary quadratic forms. In our case, we work with quinary quadratic forms. To do so, we use orthogonal modular forms, which are modular forms for the orthogonal group. For a reference, you should check the Greenberg and Boyd paper or Shefsheim thesis. Okay, so we start with the basic definitions of quadratic spaces and p-neighbors. So we start with a field K of characteristic different from 2. So a quadratic space is a finite dimensional K vector space with a function phi such that it's quadratic and the associated bilinear form that is presented here is symmetric. Okay. And if we have a basis of our space B, then we can construct a quadratic form in n variables, where n is the dimension of the space, in this fashion. Okay, and if we have different bases, we have Q equivalent quadratic forms. In fact, every quadratic forms comes from this. Well, now we define the discriminant of P to be 1/2 of the determinant of the function phi in the elements of the basis, the bilinear form in the elements of the basis. Okay. Now we define an autometry of the quadratic space to be a linear map that respects the quadratic structure of our space, like here. Now the autometries of this space, of this quadratic space, form a group with the composition as product. This group is called the orthogonal group, and we denote it by O of B. Now, if we have an autometry, then this autometry will always have determinant 1 or -1. And if the determinant of the autometry is +1, we say that the autometry is proper. The proper autometry from a subgroup of O of B, and we denote it by O plus of B. Now, a lattice in our quadratic space B is a free maximal C module lambda. In other words, lambda is isomorphic to C to the power of the dimension of the space. The lattice is integral when the phi of lambda is included in C. Well, now two lattices are properly equivalent, and we denote it by lambda tilde gamma if we have some proper autometry of our space such that sends one lattice to the other. And we denote the proper equivalence class of lambda to be square brackets of lambda. Now the genus of our lattice lambda would be all the lattices such that, all the lattices gamma such that gamma and lambda are properly equivalent for all localizations for all primes. Now the class set of lambda would be the set of proper equivalent classes in the genus of lambda, and it has a finite cardinal. Okay. Now a way to compute all the genus is using the Kneser method of p-neighbors. We now keep the definition, a more general definition for pk neighbors. So we have two integral lattices in a positive definite quadratic space, a prime P, and an integer k greater or equal to 1. We say that lambda and gamma are pk neighbors if lambda and gamma are equal for all localizations at the primes different from P, and at P we have these isomorphisms. Well, a method to compute all the P1 neighbors is using the theorem, which says that there is a bisection between the set of non-singular projective solutions of phi of P congruent to 0 mod P and the P neighbors lattices of lambda. To compute the other pk neighbors for k greater than 1, the pk neighbors are related to the isotropic subspaces mod P of dimension k. So in the case of dimension 5, which is the case that we are interested, we only have isotropic subspaces of dimension 1 or 2. So we are going to compute only that. Now, we can count the number of pk neighbors, and if P doesn't divide the discriminant of our lattice, then the number of pk neighbors of lambda is big O of P to the power of k times 4 minus k. This is for the canary case. So when k is equal to 1, we have big O of P cubed, and for k equals 2, we have big O of P to the power of 4. Okay, so now we can define the space of orthogonal modular forms. Okay, so the space of orthogonal modular forms for a lattice lambda with trivial weight is the space of functions from the class set of lambda to k, to q. In the basis of characteristic functions for the class set of lambda, we have that the space of orthogonal modular forms is isomorphic to q to the h, where h is the cardinal of the class set. Now, we can define Hecke operators in this space like this. We take P to be a prime that doesn't divide the discriminant of the lattice, and we define T, P, K, an operator that sends F to TPKF, and when we evaluate it in the class of a lattice lambda prime, then we obtain the sum of F evaluated in the class of gamma prime, where gamma prime are all of the pk neighbors of lambda prime. Well, these operators commute and are self-adjoint with respect to some inner product. This inner product is related to the number of autometries of the lattices, which is finite because we are working with positive definite quadratic forms. And we denote the S of lambda to be the orthogonal complement of the constant functions, and we call it the cuspidal subspace. This subspace has codimension 1. Now, by a conjecture of Ibukiyama and a theorem of Ladd, we expect that orthogonal modular forms, cuspidal orthogonal modular forms, for quinary lattices of prime discriminant corresponds to paramodular forms. So, we can define a map, theta. We let lambda be a quinary lattice of discriminant n, and we define the map theta to be a map from the cuspidal orthogonal modular forms to the space of modular forms of weight 5/2 and level 4n. by taking the theta series of the combination of the linear combination of classes of lattices. Now, if we have a cuspidal orthogonal modular form, which is a Hecke eigenform, then with theta of f different from 0, then the Shimura lift of the theta f is a modular form of weight 4 whose Grzynchenko lift should correspond to f, as in the following diagram. The Grzynchenko lift is a lift that sends classical modular forms of weight 4 and minus sign to paramodular forms. Okay. So, on the other hand, Hein, Ladd, and Tornaría conjecture that if we have an eigenform, a Hecke eigenform, such that theta of f is equal to 0 and n is prime, then f corresponds to a paramodular form that is not a Grzynchenko lift. So we are going to search for that in this example. We take B to be Q to the 5, a quadratic form, a quinary quadratic form of discriminant 61, and lambda to be C5. Well, this is the first example of prime discriminant on O5 for which the theta series map on the genus has a kernel. And we have here the dimensions of all the spaces. The number of classes is 8. The dimension of the modular forms of weight 4 and minus sign on level 61 is equal to 6. And the dimension of the kernel of theta is equal to 1. Well, as the kernel is non-trivial, we can take an element in the kernel, a non-zero element, which is an eigenfunction for the Hecke operator. And we can compute. We developed some code in Sage to compute this. We computed the eigenvalues for TP1 and for TP2. I believe that Ladd and Hein already computed this. So they agree with our computations. Our computations agree with them. Now, by Bukishima dimension formulas, we have that the dimension of the paramodular space of dimension of weight 3 and level 61 is equal to the dimension of the cuspidal orthogonal modular forms, which is exactly the dimension of the modular forms of weight 4 and minus sign and level 61 and the dimension of the kernel of theta. In this case, the correspondence that I mentioned before between the cuspidal orthogonal modular forms and the paramodular forms of weight 3 and level 61 should be a bijection because they have the same dimension. Okay, so now we go to another example where this fails. We take P to be Q to the 5 and a quadratic form with discriminant 167. In this case, the genus of lambda to be C5 has 19 other classes. So the dimension of the cuspidal subspace is 18, but the dimension of the paramodular space in this case is 19. So the correspondence from the cuspidal subspace to the paramodular space is not a bijection. Okay. So to overcome the missing forms, we introduce a weight to the orthogonal modular forms in this fashion. Well, we take a representation rho from the proper autometries of B to GL of W where W is a finite dimensional Q vector space. And now if we take the lambda 1 to lambda h, the representatives of the class set of lambda, we can define the orthogonal modular forms for lambda with weight rho to be similar to the previous definition. But now we take that the F takes elements from the class set of lambda to W. And we ask that the image of the class of lambda y is in the fixed subspace of W by the action of the autometries of lambda y. And this is isomorphic to the sum of W, the fixed subspaces of W of the autometries of lambda y. Now we want to define the Hecke operators, but we need the transformation matrices now. Okay, so we take P that doesn't divide the discriminant of lambda. And now if we have a gamma, a pk neighbor of lambda, we have that gamma is equal to gamma lambda chi for a unique chi, and lambda a proper autometry in the space. And this gamma is unique modulo multiplication by the proper autometries of lambda j. So we now define the Hecke operator, TPK, similarly as before, but now we act by the representation. As before, we are summing over all the pk neighbors, but we are interested now in the transformation element from one class to its neighbors. Okay, now Tornaría in his thesis uses a character of the spinor norm for the ternary case to compute modular forms of weight 2 and sign minus. This was missing from the Birch algorithm that I mentioned before, because the Birch algorithm only computes modular forms of plus sign. So with this, Tornaría was able to compute the whole space of modular forms of weight 2. So the idea is to do the same. Now we'll define this character nu, define over primes. We define it in the rationals modulo squares. We define it in primes as this. Nu d of p will be equal to -1 if p divides t, and 1 if p doesn't divide t. And we define the one-dimensional representation, rho d, to be the composition of the spinor norm with this character. Now, if we return to our example of 167, we can compute all the autometries of the lattices in the genus that we were working, and we find out that all the classes but one have an autometry with spinor norm 167. So the fixed space should be 0 for all the lattices but one. So we have that the space of cuspidal forms should with weight rho 167 is isomorphic to Q. Now, if we take any form that is not 0, we can compute some eigenvalues like this. We have computed a lot more, and I think that we are the first one to compute these eigenvalues. On the other hand, also we computed the L function the spin-Orel function of this eigenform, and it appears to be a paramodular form, to correspond to some paramodular form of minus sign. Okay. Now we did some experiments, and I'm going to talk about that. Now, if we take a prime p, we take that is lambda p to be a lattice in the unique genus of discriminant p. Now we computed for p less than 7,000 the spaces of cuspidal orthogonal modular forms with trivial weight and with non-trivial weight. And we see that the dimension, we sum the dimensions of these two spaces, and it agrees with the dimension of the paramodular form, the dimension of the paramodular forms of weight 3 and level p. So we conjecture that we obtain all the spaces. In fact, we conjecture that for a prime p, the paramodular forms of weight 3 and level p is equivariant to the sum of the cuspidal forms for lambda p with trivial weight and with non-trivial weight. Also, we conjecture that the cuspidal subspace of trivial weight corresponds to the form with plus sign on the functional equation of its associated L function. Also, with non-trivial weight, we conjecture that they should have a minus sign in the functional equation of its associated L function. Okay, this is all that I wanted to talk about. I hope to see you all next week.